Welcome to the 15th Annual Duke University Energy Conference. Today is a day full of opportunities. You'll have the opportunity to learn from influential energy leaders. You'll have the opportunity to meet companies that are paving the way in the energy transition. And you'll have the opportunity to connect with others in the energy community. Now, our conference today, the focus of our conference, it's simple. We're going to explore the policy, the technology, and the finance mechanisms, as well as the interaction between them that's necessary to drive energy innovation. We're so excited for you to be here today. We hope that you'll engage in thoughtful and meaningful discussions, and we hope you will take away something from today and our time here together. I'm Ross Fly.
And I'm Brianne Leakey, and we are your Energy Conference co-chairs. To get us started, I'd like to introduce you Thank you. To get us started, I'd like to introduce you to our Energy Conference Cabinet. Cabinet members in the audience, please raise your hands. Everyone, look around. These will be your guides for today's event. All of our Energy Conference Cabinet members will be wearing their name tags and the green ribbon marked staff beneath their name tag. So please don't hesitate to approach them if you have any questions, concerns, or anything else that you'd like to address. I'd also like to take a moment to extend our sincere appreciation to our conference sponsors. Sponsors, you are at the cornerstone of this event's success. You're enabling us to bring together the best and brightest minds to discuss the future of energy.
And with that, I will give a brief introduction to Dr. Eric Toone and then welcome him to the stage for our introducing keynote. Dr. Eric Toone is the Chief Technical Officer for Breakthrough Energy Ventures. He leads the science, technology, and engineering across the platform. He serves on the investment committee. He's responsible for the overall technical direction of Breakthrough Energy. He's a past member of the chemistry faculty here at Duke University, where he was also vice provost and director of Duke's Innovation and Entrepreneurship Institute. He's the former director of the Department of Energy's Advanced Research Program Agency for Energy, also known as ARPA-E. And he has authored nearly 300 original papers and abstracts, is listed as an inventor on over 30 patents, and is founder of 3 venture-backed pharmaceutical companies. So with that, please join me in welcoming Dr. Toone to the stage.
Well, good morning. It's wonderful to be here. And it's wonderful to see such a big group of the Duke community here excited about the opportunity ahead of us to provide energy and prosperity to the world, but in a future that doesn't have emissions associated with it. In 2015, at the COP in Paris, the leaders of the OECD world announced Mission Innovation, an incredibly ambitious plan to double their country's R&D expenditures on clean tech by the end of the decade, by 2020. At the same time and on the same stage, Bill Gates announced the creation of the Breakthrough Energy Coalition, a group of 35 of the world's wealthiest and most influential individuals that was designed to be a private sector counterpart to the public sector Mission Innovation. A year later, in 2016, a subset of that group, 20 members of the coalition, announced their first activity, the creation of Breakthrough Energy Ventures, a $1 billion clean tech venture fund that was designed to invest in technology relevant to all of the areas responsible for anthropogenic emissions. So broadly, electricity, transportation, buildings, manufacturing, and agriculture. So when you think about it, it was really an incredibly audacious thing to do, to create a venture fund in clean tech in 2016. Because 2016 was nuclear winter for clean tech investing. Nobody was investing in this space. And why was that? Well, it really was the failure of Clean Tech 1.0. So Clean Tech 1.0 started sometime early in this century. And it was the time when the venture industry, sort of flush with its success at the end of the last century, creating some of the biggest companies on earth, Google, Microsoft, Apple, Amazon, turned their attention to tough tech broadly and to clean tech in particular. And that exercise lasted about 10 years and was a complete and absolute disaster. And somewhere near $50 billion disappeared down rat holes as people discovered that the tech model of investing didn't work well for tough tech, and in particular didn't work well for climate tech. And in retrospect, the reasons for that failure are pretty obvious. The timelines don't match up. A normal venture fund is constructed on a 10-year term. That doesn't match the time constant of development of steel in the ground, tough tech kinds of projects. You need a different kind of people. You're operating in commodity markets that have razor-thin margins. It's steel in the ground. There's an enormous amount of money and different kinds of money that are necessary to make impactful advances in this space. But nonetheless, they set out to create Breakthrough. And Breakthrough was deliberately created to try and absorb the lessons of Clean Tech 1.0, right? Einstein's definition of insanity, repeating the same thing over and over again, expecting a different outcome. So the name of the game here is we're going to try and do this in a different way. And so when the current Breakthrough Energy Ventures team looks at a problem, we ask ourselves 4 questions, right? There's 4 topics that we consider. So the first is climate impact. So we sort of drew a line in the sand here and said, we will invest in any technology that we believe has entitlement to half a gigaton of emissions, CO2 equivalent emissions abatement over the course of its lifetime as it's developed fully at scale. Half a gigaton. So 1%, roughly 1% of global emissions. So that's kind of an arbitrary number. And now, of course, what happens is everybody's invention magically gets to half a gigaton. Or really not half a gigaton, it's always 0.56, right? When they come to see it, it's always 0.56. So the kind of second half of that is, you know, we tell people, and if you need a spreadsheet to show me how you get to half a gigaton, never mind, right? The point is we're supposed to be tackling the biggest, hairiest, most audacious problems there are out there. Cement, steel, those kinds of things. Climate impact. The second question we ask is this an opportunity to attract new investments to the space? Now, that was obviously a much bigger issue in 2016, 2017, because nobody was investing. So the question was, can we get people back into the game here? And as you know by now, there's an awful lot of venture investment in clean tech. But we still need more money, and we need different kinds of money. Remember that things deploy and scale differently in this space than they do in tech. These aren't iPhones or apps, right? This is steel in the ground stuff. First of a kind deployments might cost $1 billion or more. And so we need a different kind of money, a different kind of investor. We need the sovereign wealth funds. We need the pension funds. We need the Temaseks. We need that kind of money in the field. And we are now starting to see that they are coming to this space. The third question that we consider is scientific possibility, and here I think is the place where the tech model of investing most ran into trouble. You know, if we're honest about how you do tech investing, I see 50 opportunities. 43 of those, I'm pretty sure that's never going to work. The other 7, I don't know. So let's give them a little bit of time and a little bit of money and see what happens. And that works fine in tech, because a little bit of time is 6 months or a year, and a little bit of money is $500,000. The problem is when you get to clean tech, a little bit of time is 5 years and a little bit of money is $30 million. So that spray and pray approach just doesn't work. To deal with that issue, we have assembled the most technical venture firm that has ever been built on the face of the earth, right? There's no other tech fund on earth that has a professor of chemistry in it. So about 3/4 of our team, 3/4 of our partners have terminal degrees in chemistry, in math, in physics, in all branches of engineering. We are set up to go very, very, very deep on opportunities that we see. And here we are 7 years into this, and we haven't had a single company that's failed for technical issues. So scientific possibility and building a firm that's capable of evaluating the scientific possibility of these investments is something that's important. And the fourth is filling the gaps. We want to invest where other people aren't. We want to tackle the problems that other people don't want to tackle. If there's 6 or 7 firms that are fighting to get in a deal, that's not for us. We'll go someplace else. But even when you do that, that's not enough. And I hinted at this, right? How you deploy these things. These technologies have mass. And so taking them to scale is steel in the ground. It's huge money. You're often working in commodity markets where margins are razor thin, right? So you need to build a whole ecosystem. And so in addition to just the venture fund, we've tried to build that ecosystem out. So now if we look across the whole sweep of the organization, we have Breakthrough Energy Fellows, where we have a group of people that are looking at areas that we might be interested in, but we're not sure if there are scientific breakthroughs that would support the development of a technology. So all the way back to university, national lab level basic science. Is there a technology that we can build on a recent scientific discovery? I mentioned Breakthrough Energy Ventures. The venture fund we have, we've also now raised a fund that we call Select that's designed to take some of our most promising companies and start to scale those. And then I also mentioned that we need to do deployment, at-scale deployment. First-of-a-kind deployments in this space are usually not profitable. Those kinds of firms, the pension funds and things that I talked about that's necessary to do these at-scale deployments, they want to fund your third deployment, not your first. And so we built Breakthrough Energy Catalyst that provides concessionary capital to do those first-of-a-kind deployments and to start these technologies down their learning curves so that we can understand their ultimate cost entitlement. Energy, of course, operates in one of the most highly regulated markets on Earth. And so we have an energy policy and advocacy group headed up by Mike Boots that works with our companies to help them understand the nature of the regulatory structure that they're working in, and also helps to shape that regulatory structure to enable the deployment of the technologies that we're interested in. So we've tried to build a whole ecosystem to help these innovations grow up. So I mentioned 2016, the first fund was a little over $1 billion. We invested that, raised a second fund that was a little bit less than $1.5 billion. So by now, we have deployed about $2.5 billion. We've funded roughly 110 companies across all 5 areas of our mandate. Over the past year, we raised BEV3, another $1 billion fund, and we also raised BE Select. So we've been doing this for about 6 years, and it's worthwhile asking, where are we? I mean, how are we doing? What are the opportunities that we missed? What should we do going forward? And so we've been spending a lot of time doing that over the last year or so, and I want to talk to you about our thinking on that topic today. And I put these opportunities that we're sort of most interested in now into 3 big buckets. So the first one I'll call gaps. So these are areas that we knew were important when we started back in 2016, but for which we really haven't found solutions yet, right? Or at least we haven't found complete solutions yet. The second is what I'll call portfolio fast forward. So the idea here is, what are the consequences of the investments that we've made? What are the consequences of deploying the technologies that we've supported at scale? What are the new investment opportunities that arise because of deployment of those investments? And then in the third, which I've called It's Not Enough, we'll talk about areas that we just didn't see at all when we were doing this in 2016, but that we've come to realize are likely to be important. So let's think about that. The turn of the century, in 2000, there was about 17 gigawatts of wind deployed globally. 2015, when we were spinning this up, it was about 435 gigawatts of wind energy deployed globally. Now, today, there's something on the order of 900 gigawatts. But global energy generation is 7 terawatts, right? 1.7 terawatts just in the United States. It's sort of become vogue to imagine that a powerful way of decarbonizing is to electrify everything and then decarbonize the grid. Okay, that's fine. Electrifying everything and then decarbonizing the grid, how big would the grid have to be? By some estimates, we'd have to increase the size of the grid by fourfold. 7 terawatts to 28 terawatts. Can we massively increase the production of wind and solar energy? Sure we can. Can we do it by 4,000%? That's a little tricky. And remember too, let's think about cost. A lot of times when people say we're going to electrify everything, they do math on the viability of that and what the green premium associated with that might be. And you sit there and you go, well, there's people signing power purchase agreements, PPAs, for $15 a megawatt hour, 1.5 cents a kilowatt hour. $10 a megawatt hour. So the math works if I use that number. But remember, you get energy from wind and solar when the wind blows and when the sun shines. It's intermittent. For a lot of applications, intermittent electricity is not really of any value to me. I need firm, dispatchable electricity. To turn intermittent wind and solar into firm, dispatchable energy, I need storage. And storage makes that $10 a megawatt hour energy $50 a megawatt hour. And now all of a sudden it's not viable. We need enormous new amounts of zero carbon electricity on the grid. That is an enormous need. So how can we do that? Well, we've got exactly 3 sources of energy that we can tap to do that. We have the energy that arrives from the sun, we have the energy that's contained as heat in the Earth's core, and we have nuclear energy. So let's think about where we are on all of those topics. Today, energy from the sun provides about 1/4 of the planet's power, about 1/4 of the world's electricity in the form of solar PV, wind, and hydro. By now, basically all of the large-scale hydro that's available has been tapped. But that doesn't mean there's not a lot more hydro we can access, right? We can use run-of-river hydro. We can use low-head hydro. We can power unpowered dams. There's an enormous number of dams in this country that exist for navigation and flood control and irrigation. None of those dams are powered. They could be repowered. But we need a lot of new technology to develop that. We need fish-friendly turbines. We need efficient turbines that work at low heads. We need new, less disruptive ways to power unpowered dams. Accessing those forms of electricity might double the amount of electricity that we could generate from hydro without really any environmental impact. Solar PV today operates at somewhere close to 20% efficiency. It's hard to go too far beyond that, largely because the nature of the band gap of the materials that we use to collect solar PV. So think about this. I'm going to use something as a collector. It has a band gap. All of the energy, the total solar spectrum that lands on that, photons that are higher in energy than the band gap, the amount of energy above the band gap is lost as heat. Photons that are incident that are below the band gap aren't absorbed at all because of the quantum nature of light. Recently, people have been working on so-called tandem or multi-junction cells, where I put 2 different cells that have 2 different band gaps on top of each other. And if the top layer is transparent to the wavelengths that the bottom layer is going to absorb, I can do a double. I can absorb with 2 different band gaps. There's a number of people that are working on that today. But it's hard to come up with these collectors. It's hard to make these collectors robust enough that they'll have 20-year lifetimes, all of those sorts of things. There's an enormous amount of research that needs to be done to make better solar collectors. And remember, the name of the game isn't efficiency, and these things are certainly efficient. We can increase the efficiency of solar by 50%, and in fact, devices that have an overall efficiency of 50% have been prepared. But efficiency isn't the name of the game. Cost is the name of the game. Cost is absolutely the name of the game. And so as you increase the efficiency, other parts of the value chain become the long pole in the tent. Trackers, steel in the ground, installation, all ripe for technological innovation. Solar energy applied unevenly across the Earth's surface produces weather. That weather produces wind, which we capture with windmills today, but it also produces waves. Right? So there is an enormous amount of energy contained in waves that are produced by wind. Capturing that energy is very difficult. But people are working on this. An Australian company, Waveswell, recently reported a turbine that captures the energy from waves. The Australian Science Agency, CSIRO, confirmed that they can do that for as little as 3.2 cents a kilowatt hour. That's pretty good, but a lot more work to be done there. And not just waves. There's an enormous amount of energy contained in the currents that flow in the ocean. By some estimates, as much as 5 terawatts. 5 terawatts. Just in the Gulf Stream, there's as much energy as 21,000 Niagara Falls, more than 50 times the energy contained in all the Earth's rivers. But we don't have any technology that's capable of capturing the energy from ocean currents. And then finally, there's an enormous temperature gradient between the warm water on the surface of the ocean and the cold deep water. Ocean thermal energy conversion, or OTEC, could conceivably add as much as 7 terawatts to the global generating capacity. but we really have no way to capture that ocean thermal energy today. Another area that's enormously ripe for innovation. And then there's the energy that's contained in the heat, as heat in the Earth's core. We know that the way we get this out is with geothermal. Conventional geothermal requires three things. It requires heat, it requires porosity, it requires water. And if you have to look for places that have all three of those elements, the technical resource is really pretty small, probably something on the order of 50 gigawatts in the United States. Advanced geothermal, where I find rock that's hot, induce porosity, and add water, massively increases that potential, and we're working on that today. That needs new drilling techniques. And drilling techniques that worked at high temperature, right, drilling really still doesn't work very well much above about 250 degrees Celsius, right? And so high temperature drilling would massively increase the resource of geothermal energy on Earth today. And then we have nuclear processes, okay? So nuclear processes convert very small amounts of mass into energy, according to Einstein's famous formula of E equals mc squared. Because of the nature of that formula, the conversion of even very small amounts of mass into energy releases enormous amounts of energy. In fact, the conversion of just 1 ton of mass into energy would power the entire planet for a year. That is the appeal of nuclear energy, right? We can do nuclear energy in two ways. We can take a heavy nucleus and split it into 2 lighter nuclei, where the mass of the 2 lighter nuclei adds up to less than the mass of the nucleus that I started with. That is nuclear fission. Alternatively, I can take 2 light nuclei and fuse them together into a heavy nucleus, where the mass of the heavy nucleus adds up to less than the sum of the 2 light nuclei that I started with. Today, nuclear fission provides about 10% of the planet's energy. That number has been constant or even declining slightly, effectively since the time of 3 Mile Island. And the reason for that is after 3 Mile Island, the cost of building and deploying nuclear fission went up roughly fivefold. And so the problem with nuclear today is cost. And that cost is attributable to the nature of the reaction. Nuclear fission is dangerous. Nuclear fission is dangerous. The nuclei that I produce when I break a heavy nucleus into 2 lighter nuclei are radioactive, and they stay radioactive for millennia. They have to be stored for very, very, very long times. The nuclei that I produce are fissile and can be used to produce weapons. And because it's a chain reaction, I always have the danger of a thermal runaway, which is basically what happened at 3 Mile Island. It is our belief that the problem with fission is you're stuck in this paradox: waste, safety, proliferation. And there's no way out of that box. And so because it's inherently dangerous, it's inherently expensive. We have instead chosen to focus on fusion because it avoids all 3 of those problems. The radioactive nuclei that are produced are radioactive for decades, not millennia. They are not fissile, and they can't be used to build weapons. And it's not a chain reaction, and so there is no problem with thermal runaway reactions. Now, that doesn't mean fusion's gonna be cheap. Don't get me wrong. That sure as hell doesn't mean fusion is gonna be cheap. It just means you're not stuck in a paradox where it can't be cheap. Fusion, of course, happens at extremely high temperatures. I have to strip the electrons away from the nuclei and create a plasma. The temperatures that you need to do that at are too high to contain this in a physical vessel, right? It's millions of degrees. I can't contain it in a physical vessel. And so what I have to do is contain it in a magnetic field where it doesn't actually touch anything. The field of nuclear fusion advanced massively with the development of high TC superconducting tapes that can be fashioned into the magnets that build a plasma that I can work with. And today there are really 2, and we're supporting both of these companies, 2 that are especially attractive. So the geometry on the left is a tokamak. So this is the easiest magnet to build. This is the easiest kind of magnet to build, and it creates that spherical that spherical plasma. There have been over 200 tokamaks built and operated around the world by now, and many of those have been at or really could have gone above the breakthrough threshold for fusion. Again, what changed everything, when I build a device out of this tokamak using these high TC magnets, it would fit in this room, as opposed to ITER, which everybody has seen takes up, you know, acres and acres. The geometry on the left here, or on the right here, is called a stellarator. So this is a toroidal field, and there are reasons that you would want to use that instead of a tokamak. Basically, a tokamak is easy to build, but because of field instabilities, it might be hard to operate. A stellarator is really hard to build, but that toroidal geometry is much more stable. Last year in Germany, folks built a tokamak and operated it, and so we know now that with these new magnetic materials, we can build these things. But this is just the start. There's an enormous amount of work that needs to be done still to turn fusion into a practical reality. Once you've got a device and it's operating, that's not a power plant. So you have to think about how you're going to turn that into a power plant. And there are other designs: inertial confinement, laser-based fusion, all sorts of things, an enormous amount of technology that can be developed here that would provide huge amounts of electricity to our grid. Whatever else you think about Elon Musk, he changed the face of transportation forever with the introduction of the Tesla Roadster and the later models. And what changed here? Okay, the important change here, and I think really Elon's biggest contribution to this whole game, is he changed our perception of electric vehicles, what they are. They're not golf carts, they're not toys. They're badass, right? They're things you want because you want that car. You don't care that it's electric. You're not buying it because it's electric. You're buying it because you want to play with it, because it's fun. It's a fantastic example of where the electric replacement, the electric alternative, is better than what you started with. But adoption of electric vehicles has been slow, right? About 80 million vehicles sold globally last year. About 10 million of them were electric, mostly in China. Right? I read in the New York Times this morning that we're on track in this country to sell 1 million EVs in the United States for the first time ever. Adoption has been slow. And there are big chunks of transportation that are going to be very, very difficult to electrify. Flight, aviation, especially long-distance aviation, long-haul shipping, long-distance trucking. And remember that there are 1 billion gasoline and light truck vehicles, internal combustion engine vehicles, on the road today that all use gasoline. They use gasoline because of the energy density of gasoline, right? Remember that in transportation, I got to haul my energy around with me. And so density becomes a big deal, both gravimetric and volumetric. The energy density of the batteries that go into Teslas today, about 350 watt-hours per kilogram. The energy density of gasoline, 14,000 watt-hours per kilogram, right? We don't use gasoline and diesel because we're dumb. We use gasoline and diesel because if you gave a whole bunch of the world's smartest scientists and engineers an infinite amount of money and an infinite amount of time and said, come up with the perfect energy storage medium for transportation, they'd come up with gasoline and diesel. We need new ways to make liquid fuels. Liquid fuels are going to be with us for a very, very, very long time. So how are we going to do that? Well, one way we can do that is biofuels. So I can use photosynthesis to capture energy from the sun, store it in chemical bonds. That's an incredibly inefficient process. Photosynthesis operates at way less than 1% efficiency, way less than 1% efficiency. And it uses enormous amounts of water. Today, roughly a third of all cropland in the United States is planted with corn. 40% of that corn goes to make biofuels. And that corn makes 5% of the nation's liquid fuels. It doesn't even come close to passing the giggle test, right? There is no way this scales. Farm subsidies are a great thing in Iowa, but there is no way this scales. If we're going to use photosynthesis, we need new organisms that are vastly more efficient. We need new organisms that don't need fresh water. We need a whole different approach to biofuels if this is ever going to scale and be an important part of the energy economy. Or I could use electrofuels. So I could take hydrogen and react that with CO2 to make syngas, and then use Fischer-Tropsch technology or other technology to turn that syngas into liquid fuels. We know how to do that, okay? It all comes down to a question of cost. So let's think about what our cost targets are going to be if this is how we're going to do it. Well, the alternative to making liquid fuels, the alternative to making zero carbon liquid fuels would be to keep drilling stuff out of the ground the way that we do now, and then do post-combustion air capture. So what does that cost? Well, if I say long-term stable price of oil, $60 a barrel, put whatever you want in as a crack spread, $15 a barrel, and let's say $200 a ton to do post-combustion air capture of CO2. That gets you to $4 a gallon. Okay, so that's what my price target is going to be. If I say I'm technology agnostic, I just want to do this the cheapest zero carbon way that I can do it. Well, all right, so if I'm going to make zero carbon fuels, bioelectric fuels, I still got to do the air capture CO2 because I need my carbon from someplace. So $200 a ton, that's about $1.50 a gallon. The energy content of a gallon of gasoline and a kilogram of hydrogen are almost exactly the same. Okay, it's a sort of a useful statistic. So you're going to need a little bit more than a kilogram of hydrogen. Well, how am I going to make my hydrogen? If it's going to be zero carbon, electrochemically, I'm going to use electrolyzers to make it. Okay, it takes 52 kilowatt hours to make a kilogram of hydrogen electrolytically. If I'm paying 2 cents a kilowatt hour for my electricity, there goes another buck. It's hard to do. This is hard to do in a cost-competitive fashion. There's an enormous amount of technology that's necessary to drive the cost of hydrogen down below $1 a kilogram, enormous amount of technology necessary to do air capture down below $100 a ton. So a huge opportunity, huge effort there. Or maybe we could just get rid of transportation. Maybe we could just get rid of travel, right? 2020, we were all part of one of the most amazing sociological experiments that's ever been done on the face of the earth, right? The pandemic descended, and we all packed up, went home, and worked from home for 2 years. But then we get to 2022, the pandemic lifts, and everybody goes back to work. Or at least goes back to work part-time. Well, why did we do that? Why didn't we just stay home and keep working from home? Well, because we discovered that communication, interpersonal interaction over computers isn't the same as interpersonal interaction. There are really important aspects of communication, things like eye contact, gaze behavior, pupil dilation, that are important to how we perceive each other, that don't translate to 2 dimensions in shitty little screens. There's important aspects of audible communication, prosody, nonverbal sounds, things like that, that don't come across on those little microphones. So that's why we all went back to work, because we need to be with each other to properly communicate. Today, there are an enormous number of computer scientists and social science scientists that are working to better understand the nature of social presence and to think about how we can replicate it in 2 dimensions, right? So augmented reality, virtual reality, all of these kinds of things, the immersive internet, the metaverse, will be incredibly important to improving the way that we replicate that social interaction and obviate the need for travel by allowing us to do more effective at-distance communication. All right, so those are some of the things that we knew were problematic and we haven't found good solutions for yet, and that we'll keep working on. What about things that are the consequence of some of the things that we've been working on going forward? What are some opportunities that open up because of that? Well, let's think about a few of those. The first is unquestionably the grid. I said that if we're going to electrify everything, we probably need to make the grid on the order of 4 times bigger than it is today. 4 times. That means massive expansion of the grid. The grid today is a bunch of dumb wires hung on poles. We attach loads, generation gets dumped onto them, and the electrons just magically find their way inductively by the path of lowest resistance to where they go. There's no single agency that's responsible for the operation of the grid. No single agency that's responsible for the maintenance of the grid. We can't even model the grid today. We don't even really know how it works. The grid of tomorrow will look nothing at all like the grid of today. We need massive new amounts of generation. You know, I read the other day somebody suggested that we may need as much as 80 million kilometers of new or refurbished transmission by 2040. 80 million kilometers. That's to the moon and back 100 times. How are you going to do that? We can't permit transmission in Vermont, for crying out loud. We need new conductors that carry vastly more energy than the conductors that we use today. We need wireless transmission. We need a whole new generation of power electronics to control those flows. IGBTs, IGCTs, ETO thyristors, MOSFET switching devices, faster switches, switches that work at higher voltage and higher current, elements that work near the edge of the grid, autonomous restarts of the grid. Whole new set of generation that needs to be created and deployed to build out the grid of the future. Let's think about another consequence of electrifying everything. Another massive consequence of electrify everything is, where are we going to get the elements that we need to do it? Right? There's been a massive increase in the use of lithium for the development of lithium-ion batteries, and the price of lithium recently rose 6-fold over a 15-month period. Right? Important suppliers like Bosch have started warning against an over-reliance on lithium-based devices. Where are we going to get that? And it's not just lithium. It's the cobalt and nickel, and not just battery materials. It's platinum group elements and osmium for catalysis. It's neodymium and dysprosium for the high-strength magnets that we need to build motors and generators. In 2010, in fact, Eric was probably involved, there was a report at the Department of Energy that warned about coming shortages of neodymium and dysprosium specifically. And here we are 13 years later, we're in exactly the same place as we were before. There's an enormous need for critical materials. So where do we get those critical materials? Well, we need new ways to find those critical materials, and we're funding a number of companies that have novel ways to identify mineral deposits. But once you find them, you got to get them out of the ground. And how do we get them out of the ground today? Well, we build mines. And that's tough, man. That is tough. From an environmental perspective, this is big, dirty work. And you recently saw, I'm sure, that they couldn't permit mines in Greenland. If you can't permit mines in Greenland, where are you going to build mines exactly? We need new approaches to mining. We need environmentally benign ways to extract the elements. Biomining, where we use microorganisms and plants to concentrate metals. And some of those organisms are already used in mining things like cobalt and gold. We need to access sources of minerals like mine tailings so that I don't have to build new mines. We need to go to new places. Can I concentrate minerals out of the ocean? I'm sure many of you have seen these polymetallic nodules that sit on the bottom of the ocean floor in the Pacific. China is working hard to access those because they may be important sources of minerals. The cost of space launch, the cost of space lift has dropped by 3 orders of magnitude over the last 20 years. Might we someday be able to mine asteroids? It's possible. It's not crazy. Of course, all the ways that we mine today involve some combination of gravity and water. So that might be a problem for asteroids too. Huge amount of technology that needs to be developed in finding these critical materials and then figuring out ways to extract them once we find them. And while we're thinking about big industrial processes, about half of all the energy that we use in our society is as heat. Okay? Half of all the emissions that come from industry are from heat. A lot of that heat, a little bit more than half, is at relatively low temperature, below about 400 degrees Celsius. At those temperatures, you can develop high-efficiency heat pumps and things like that to electrify the production of that heat. But a third of industrial processes operate above 1,000 degrees C, and some, like glass, operate above 1,400 degrees C. That's tough to electrify. That is really tough to electrify. And we are both blessed and cursed to live in a geography that has enormous quantities of incredibly cheap natural gas, right? At $3 a million, if you were going to electrify 1,000-degree heat and have it cost competitive with $3 a million natural gas, 2 cents a kilowatt hour is what you need for electricity. And that's firm, right? A process that's operating at 1,000 degrees can't get turned on and off. It needs to run full time. Electrifying heat is one of the toughest problems that we have, but it's a huge contributor to emissions, and we have to figure out how to get that done. Yeah, and so then while we're at it here too, this one, like, the hardest thing there is to do in the whole energy game is to wrap your head around the concept of scale. We do energy that dwarfs, at scales that dwarf any other human activity. And it's almost literally impossible to comprehend. So I collect these little vignettes to try and impress on people what we mean when we talk about scale when we're talking about energy. And this is one of my favorites. The Hebron Ben Nevis oil field is an oil field off the coast of Nova Scotia in Canada. It was discovered in the 1980s. It's being developed by ExxonMobil, Chevron, and others. They expect it'll cost something like $10 billion to open and operate that oil field over the course of its life. That life is expected at 30 years. So think about that. We're hiring young men and women to go work on this project who will spend their entire working lives working on this project. Over the course of its life, it's expected to produce about 750 million barrels of oil. That's 8 days of global supply. That's what scale means when we're talking about energy. It's almost impossible to conceive. And so the idea that you can do this in a way that has zero environmental impact on anything, stop it. Just stop it. You can't. This is big, big, big scale. It's steel in the ground stuff. It's hard, and we have to come to grips with that. All right. Well, what are the things that we weren't even contemplating when we started out all those years ago? 1987 in Mali in North Africa, a group of villagers were drilling a well for water. They went down 106 meters, the well exploded. They assumed they drilled into natural gas, they plugged the well. 2012, a group went back and opened that well to start extracting the natural gas. They started collecting it and said, wait a minute, that's not natural gas, it's hydrogen, pure hydrogen, coming out of the ground. Since that time, an enormous number of seeps have been discovered all over the world. In fact, the original Olympic flame that's been burning in Turkey for 3,000 years is burning hydrogen, not natural gas. That hydrogen, this turns everything that you've ever read about hydrogen on its head. All the textbooks say hydrogen's not a primary source of energy, it's an energy carrier. Yeah, it's a primary source of energy. There are all sorts of theories about how this hydrogen is produced. The one we believe, and I think the most likely one, is that it's the reaction of iron 2 of reduced iron in the Earth's crust with water. If that's what it is, then this is almost limitless. Really, it is effectively limitless. Jeff Ellis at the United States Geological Survey recently said that he believes the available resource, not the technical resource, but the resource we can actually access, may be as much as 1 trillion tons. 1 trillion tons. That's enough to power all humanity for several thousand years. This will be the most important discovery in energy in our lifetimes, right? Infinite zero carbon hydrogen at less than $1 a kilogram. And we're working on this in an enormous way. But it's pretty clear by now that getting there is going to be well nigh impossible, right? If you consider getting there to be 1.5 C, it's just not going to happen. Even 2 degrees C looks like it's awful difficult. John Holdren famously said that when it comes to climate, we have exactly 3 choices. We have mitigation, adaptation, and suffering. Mitigation's not going to be enough, and suffering's unacceptable. We're left with adaptation. And so as we go forward into Fund 3 and beyond, we will start working on adaptation. So what kinds of things might that involve? With increasing temperatures, plants don't do very well, right? Seeds fail to germinate. Plants grow too fast. Florets fail to develop seeds. Crops fail. The pollinators that pollinate those plants start to fail as well. Colony collapse disorder has become a growing problem among honeybees. But plants have specific mechanisms by which they defend themselves against rising temperatures. They grow to increase convection. They use evaporative cooling. They grow to provide greater shade to the plant. Those traits have a significant genetic basis, and they're collectively referred to as thermomorphogenesis. So we can copy those traits into plants that produce food and perhaps make plants that are more resistant to rising temperatures. And what about those pollinators? What do we do about them? You know, releasing genetically modified insects into the environment is a scary thing to do. But, you know, these pollinators pollinate 1/3 of the world's crops. Life without them on this planet is not tenable. Recently in Florida, mosquitoes were introduced into the wild to contain a kill switch. Is it possible to introduce something like that into these bees so you could use genetically modified organisms better capable of dealing with temperature, but that couldn't propagate? I don't know, but I think we need to check. Or maybe we just stop growing plants in fields. That might be a good way to do things, right? We already use indoor agriculture for a variety of fruits and vegetables, and we can increase productivities by 10x and massively reduce the amount of both land and water that we need. But if you think about what really feeds this planet, right? Corn, wheat, rice, starch, the alpha-1,4 polymer of glucose provides 42% of global calories. You're not going to grow wheat indoors. Recently, a Chinese group demonstrated a non-natural sequence of just 9 enzymes that converted formaldehyde into starch. It does it at 10 times the rate that a plant makes starch, and obviously it uses much less water. Could you ever make that process economically viable? I don't know, but I think we better start looking. About 80% of global commerce by volume, about 70% by value, moves around the world by ship. That's how stuff really moves around this planet. That activity is supported by a group of about 2,000 ports that load and unload these ships and deliver them to the consumers. Many of our most important cities have grown up around those ports. By nature, they obviously have to be close to the water. Most of these ports are designed to stand a 100-year event. But when 100-year events start happening every 2 years, and the definition of a 100-year event changes massively, we have to really rethink the way that we do this. We have to rethink supply chains. We have to build new technology. We need cranes that can withstand higher winds. We need doors that protect ports from oceans. We need slope and hill erosion control. We need new warning systems, all sorts of new technology to deal with the fact that the way we move things around the planet is going to become untenable quickly. And then finally, and this again is one that I'd really like you to take away, we have to figure out how to make these technologies available in the developing and emerging world. Emissions is not an OECD problem. Emissions in the OECD world have been steady or even declining over the last few years. Where this whole thing explodes is when the non-OECD world seeks OECD standards of living, and they will do it. And if we don't provide them an alternative without a green premium, they're going to do things exactly the same way that we did, right? As people acquire wealth, they want the things that produce emissions. As people acquire wealth, they want shelter. And so in just 3 years, between 2011 and 2013, China used more cement than the United States did in a century. And that'll happen in every geography as people seek shelter. As people acquire wealth, they want calories. They want meat. And so we grow more cows, 1 billion cows on Earth now. And the methane they belch is responsible for 16% of global emissions. As people acquire wealth, they want transportation. They want mobility. And so they buy cars. And there's some economists that use the per capita number of cars and light trucks in a population as a measure of the size of the middle class. As people acquire wealth, they want cooling, and on and on and on and on. If we don't find a way to get these technologies to this group of people, and without a green premium, they're going to say, I'm building coal plants. We have to do it. We have to do it. Well, I hope I've told you today, or helped you understand today, there are enormous challenges, but with challenges come opportunities. And we're really excited about these opportunities. We look forward to working with all of you to make these and many other technologies a reality. Thanks very much for your time this morning. I think we have time for a question or two.
One of the questions that we have received from the audience: why are we still trying to mine for more instead of looking for ways to recover what's already been used? That's a great question. That's absolutely a great question. And reusing materials is something that we absolutely have to do. We are investors in a company called Redwood Materials. J.B. Strobel, who came
from Tesla that is working to recovery battery materials. So yes, 100% we have to keep doing that, but we still need a vast array of new sources of material, yes.
Well, thank you for answering that question. Another question that we have received is, why does the geothermal energy work, and what are some of the challenges that is stopping ocean thermal energy from becoming more feasible?
Okay, so a couple of questions in there. So, you know, what I need from geothermal is basically heat. If you think about most of the ways we make electricity, we take heat, we use heat to run turbines, rotating machinery, drives generators, and produces AC current. So what I need from geothermal is heat. Okay? If I'm in a power plant, the steam that I use in a power plant is probably going to be 550, 600 degrees Celsius. Pretty much the hottest material I can get out of the ground in geothermal is on the order of 200 or 250 degrees C. So I don't have very much heat, and that means the efficiency of generation is necessarily lower. What we need more than anything, it's not like we don't know where hot rock is, we just don't have technologies that are capable of operating, drilling in hot rock. So new drilling technologies that are compatible with high temperature are something that we need. OTEC is a great one on paper, but there's a couple of problems with OTEC. You know, first of all, the distances you're talking about moving water are kilometers, right? The distance between the warm surface and the deep, cold ocean are kilometers, right? So that's definitely an issue. And then the ocean is just an incredibly inhospitable environment to operate in. It's really, really, really hard. And so, you know, we need a lot of technology to make OTEC a practical reality.
And we can take one more question. How do we get the major oil companies to adopt emerging low-carbon technologies that don't have proven supply chains or economies of scale?
Yeah. So, you know, it may be heresy, but, you know, we really believe that the major oil companies are going to be important players in this transition. And the reason that I say that is because oil companies are some of the very few people on Earth who understand what scale means and who know how to operate at scale. And so we work very closely with ExxonMobil. We work very closely with Shell. We have oil companies that are investors in some of our funds. I don't believe that the oil companies are necessarily wed to continuing on with legacy resources, but they do understand the realities of doing this at scale and what it means. And so we need to offer practical technologies to them, and I think that they can be important partners in scaling those technologies.
Q&A for this session, and thank you so much.
Thanks very much.